Welcome to Chapter 1, Squares and Cubes. Let's discover the secrets of square numbers, cube numbers, square roots, and cube roots in the easiest way. Let's begin.
Welcome to this explainer. Today, we're going to unlock a fascinating mathematical puzzle hidden inside an ancient royal riddle. Okay, let's dive straight into this. We're going to look at how a seemingly impossible test of logic perfectly uncovers some of the absolute most beautiful patterns in numbers. So imagine for a second that you are competing against a prince to inherit a priceless treasure. The clock's ticking, the pressure is totally on, and all that stands between you and unbelievable wealth is a single puzzle. Let's see if your logical mind can crack this riddle first. Here's the setup. Queen Rathnamandjari has hidden her incredibly valuable jewels in a room filled with 100 lockers. She set up this massive test for her son, Prince Koisnam, and 99 of her greedy relatives. The stakes? All or nothing. Whoever solves the secret of the locker room first gets the whole shebang. Now, to actually get the treasure, they have to follow a very specific set of rules. Think of it kind of like a massive relay. Person 1 walks into the room and simply opens every single locker. Then person 2 walks in and toggles every second locker, meaning if it's open, they close it. If it's closed, they open it. Then person 3 toggles every third locker, person 4 toggles every fourth locker, and this whole thing continues, perfectly in sequence, until all 100 people have taken their turn. At the very end of this totally chaotic process, only a few specific lockers will remain open. Now, you might be thinking of just guessing, but if you do, you're going to fail for sure. The crucial point here is figuring out exactly how many times each individual locker is toggled open or closed. If we know the number of toggles for a specific locker, well, then we know its final state. And this brilliantly illustrates our very first breakthrough. Let's directly compare locker 6 and locker 9. You see, the number of times a locker is toggled is exactly equal to its number of mathematical factors. For locker 6, the factors are 1, 2, 3, and 6. That's an even number of factors, 4 of them, meaning it gets toggled 4 times and ends up closed. But look at locker 9. Its factors are 1, 3, and 9. That is an odd number of factors, just 3. So it's toggled an odd number of times, meaning it ends up open. So this brings us to a massive realization. A locker only stays open at the very end of this game if it's toggled an odd number of times. And the only way that happens is if its locker number has an odd number of factors. So the question kind of shifts. What kind of numbers have an odd number of factors? Well, factors almost always come in pairs. Think about it. For 6, it's 1 times 6 and 2 times 3. They pair up. But when a number is created by multiplying a value by itself, like 3 times 3 equals 9, that pair is actually just a single number repeated. This breaks the pairing rule and creates an odd number of factors. In mathematics, these special numbers are called perfect squares. Prince Koisnam realized this instantly. He didn't need to run around the room frantically opening and closing doors. He just did the math. He knew that only the lockers with perfect square numbers will remain open at the very end. Locker 1, locker 4, locker 9, 16, 25, 36, and so on. He cracked the code without even breaking a sweat. But the queen left one final trick. As a fun little bonus, she left a passcode protected in the open lockers. The clue states the passcode involves the first 5 lockers touched exactly twice. What numbers have exactly 2 factors, just 1 in themselves? Prime numbers. So the passcode is simply the first 5 prime numbers, 2, 3, 5, 7, and 11. Section 1, Beyond the Lockers, the Magic of Squares. Now that we've secured the queen's jewels, let's explore how perfect squares follow some truly incredible rules. What's really interesting here is how we can easily identify square numbers just by looking at their ending digits. There's a secret language to numbers, and honestly, once you see the pattern, you can't unsee it. If we look at the first 10 perfect squares, scan the ending digits. Look at 1, 4, 9, 16, 25, all the way to 100. Notice which numbers consistently show up at the very end of these values. Did you catch it? You'll notice perfect squares only ever end in 0, 1, 4, 5, 6, or 9. They absolutely never end in 2, 3, 7, or 8. This means if someone throws a massive number at you, say 5,432, you know instantly, without doing any heavy math, that it is not a perfect square, simply because it ends in a 2. And hey, The pattern holds up for zeros too. If a number ends in 10, like 10, its square ends in 2 zeros, making 100. If it ends in 2 zeros, like 100, its square ends in 4 zeros, making 10,000. Because of this multiplication effect, perfect squares will always have an even number of zeros at the end. Section 2. Squares and odd numbers. Let's look at one last mind-bending math trick between perfect squares and the absolute simplest odd numbers we know. Watch how this builds step by step. If we start with the first odd number, 1, well, 1 equals 1, which is a square. Add the next odd number, 1 plus 3 equals 4, another square. Add the next, 1 plus 3 plus 5 equals 9, and 1 plus 3 plus 5 plus 7 equals 16. Do you see what's happening here? This visual proof is absolutely mind-blowing. It shows that adding sequential odd numbers always perfectly constructs the next square. You can literally build perfect squares from the ground up just by stacking odd numbers together. And the best part is, you can even reverse this trick to test if a number is a square. Let's test the number 38. By continually subtracting consecutive odd numbers starting from 1, 38 minus 1 is 37, minus 3 is 34, minus 5 is 29, minus 7 is 22, minus 9 is 13, minus 11 is 2. The next odd number to subtract would be 13, taking us into the negatives at negative 11. We don't hit 0 cleanly. Because we skipped right over 0, this mathematically proves 38 is definitely not a perfect square. We've gone from cracking a royal locker puzzle to decoding the very DNA of perfect squares. I'm going to leave you with this final challenge to test your brand new pattern recognition skills. Based on everything we've looked at today, how many square numbers are hiding out there between 901 and 1000? Think about those ending digits, think about those patterns, and see if you can claim the mathematical treasure for yourself. Thanks for joining me on this explainer, and keep exploring the patterns all around you. Welcome to this explainer. Okay, so have you ever looked at a page full of numbers and just seen, well, flat, boring calculations? I know I have. But today, we're going to completely flip that perspective. We're going to see how abstract numbers actually have physical shapes. Yep, we're taking math off the flat piece of paper and building it right into fascinating, real-world, three-dimensional realities. Get ready to see numbers like you literally never have before. So here's our roadmap through these mathematical dimensions. We'll start with squares and triangular numbers, then move into understanding square roots, finding perfect squares, and estimating those square roots. After that, an introduction to cubes, and finally, the legendary story of Ramanujan and the number 1729. Let's jump right in. Section 1. Squares and triangular numbers. Okay, let's dive into this. To really understand the geometry of numbers, we got to start with the absolute most foundational idea, which is that numbers can actually be built out of simple dots. If you take those dots and arrange them into the shape of a triangle, you get what mathematicians call, appropriately enough, triangular numbers. We're talking about numbers like 1, 3, 6, 10, and 15.
And there is just an amazing visual connection here. If you take two consecutive triangular numbers, like say 1 and 3, or 6 and 10, and literally push them together, they form a perfect square. For example, add the triangular number 1 to the triangular number 3, and you get 4, which makes a perfectly neat 2 by 2 square. Add 3 and 6, you get 9, a 3 by 3 square. Add 6 and 10, you get 16. It's like a giant puzzle. It brilliantly illustrates how entirely different shapes of numbers just snap together perfectly like geometric puzzle pieces.
Moving on to Section 2, understanding square roots. So we've just seen the full, beautiful shape of a perfect square. But what if we want to work backward? What if we already know the total area, and we need to figure out the exact length of just one of its sides? Well, that brings us straight to square roots. Just grounding the math in physical area for a second, if a square has an area of 49 square centimeters, we automatically know the side length absolutely must be 7 centimeters. Why? Because 7 times 7 is 49. But, math has this sort of dual nature to it. Notice the positive and negative roots here. Sure, 8 times 8 gives you 64, but a negative 8 multiplied by a negative 8, that also gives you 64. So the absolutely crucial point here is that mathematically, every positive number actually has 2 square roots, one positive and one negative. However, and this is a big however, when we're dealing with physical measurements in the real world, like measuring a piece of cloth to cut, we only ever use the positive root. I mean, you can't exactly have negative 8 centimeters of fabric, right? All right, Section 3, finding perfect squares. This brings up an incredibly practical question. If I just hand you a large, totally random number, say 576 or 327, how can you quickly look at it and know for absolute sure if it's a perfect mathematical square? I mean, we can't just guess, and drawing out hundreds of little dots definitely isn't going to work. Well, here is a brilliant, honestly, almost magical math hack called the repeated subtraction method. You basically just take your number, let's use 81 for this example, and you repeatedly subtract consecutive odd numbers. So 81 minus 1 is 80. Then 80 minus the next odd number, 3, is 77. 77 minus 5 is 72. And you just keep doing this until you hit exactly 0. If you do hit 0, boom, it's a perfect square. And here's the absolute best part. The number of subtraction steps it actually took to get down to 0, that is your exact square root. So for 81, it takes exactly 9 steps. But let's be totally honest here. Actually subtracting odd numbers from a massive number like 324, yeah, that would take forever. The much more efficient way is prime factorization. Basically, we break 324 down into its most basic prime building blocks. 2 times 2 times 3 times 3 times 3 times 3. Now, if we can group these identical numbers into 2 perfectly matching pairs, which in this case we can do as 2 groups of 2 times 3 times 3, then we have our proof. Each group multiplies out to 18. Therefore, we know for a fact that 324 is the perfect square of 18. On to section 4, estimating square roots. Okay, let's step out of the pristine, clean world of perfect math and jump into the messy real world. What happens when our numbers just don't form perfect, beautiful geometric squares? Well, we need to learn how to estimate.
Imagine two friends, let's call them Aribam and Bijou, and they're playing this rapid-fire numbers game. Aribam says a number, Bijou shouts the square root. Aribam says 25, Bijou shouts 5. Aribam says 81, Bijou shouts 9. Easy, right? But then Aribam asks this exact question. What is the square root of 250? Suddenly, Bijou is stuck. 250 is definitely not a perfect square.
So how does Bijou logically estimate the answer here? Well, first he just brackets the messy number between known perfect squares. He already knows 15 squared is 225 and 16 squared is 256. Therefore, logically, the square root of 250 has to live somewhere right between 15 and 16. And since 250 is way closer to 256 than it is to 225, Bijou can confidently deduce that the square root is going to be just under 16. It's a fantastic, super practical logical tool for navigating all those messy real-world numbers. Section 5, Introduction to Cubes. All right, now it's time to really escalate our journey. I'm inviting you to step completely out of the flat, two-dimensional shapes we've been looking at so far and jump headfirst into the three-dimensional world. Welcome to the cube. Geometrically speaking, a cube is a 3D object where the length, the width, and the height are all exactly equal. Mathematically, that just means multiplying a number by itself 3 times. But think about what this actually means physically. If you have a larger volume with a side length of 4, you multiply 4 times 4 times 4. That means this larger cube literally contains 64 smaller 1-unit cubes perfectly packed inside of it. How cool is that? And you've got to notice the patterns these 3D numbers create. Take a really close look at the ending digits of those cubes. Remember earlier, we learned that perfect squares can only end in 0, 1, 4, 5, 6, or 9. But look at the cube numbers. We see numbers ending in 8, 7, 4, 5, 6, 3, 2, and 9. This definitively proves that unlike squares, perfect cubes can actually end in numbers like 2, 3, 7, and 8. The whole dimensional shift literally changes the fundamental rules of the mathematical patterns. Which brings us to Section 6, Ramanujan and 1729. To wrap up this explainer today, I really want to bring a highly memorable, very human, and historical element to all these heavy three-dimensional calculations. Because, math isn't just numbers on a page. It's the stories of the brilliant people who saw the world through them. Just picture the scene. The year is right around 1918. The legendary Indian mathematician Srinivasa Ramanujan is terribly ill in a hospital bed in England. His friend and colleague, the brilliant British mathematician G.H. Hardy, comes to visit him. Just trying to make some light small talk, Hardy complains about the ride over. He tells Ramanujan that the number of the taxicab he rode in was 1729. Hardy grumbled that it just seemed to be a completely dull, boring, and utterly uninteresting number. Even while sick in his bed, Ramanujan's brain instantly processed the three-dimensional geometry of that number. He looked right at Hardy and delivered this legendary reply. No, it is a very interesting number. It is the smallest number expressible as the sum of 2 cubes in 2 different ways. I mean, just think about that for a second. Right off the top of his head, Ramanujan realized that 1729 is exactly equal to 12 cubed plus 1 cubed, and it's also exactly equal to 10 cubed plus 9 cubed. With just one brilliant off-the-cuff observation, he transformed 1729 into the world-famous taxicab number.
And that right there is the true magic of understanding math in dimensions. When you stop looking at numbers as just flat calculations and really start seeing them as squares, cubes, and physical geometric realities, entirely new worlds of logic just open up. So I'll leave you with this provocative thought. If Ramanujan could see two sets of three-dimensional cubes hiding inside the number 1729 from a hospital bed, what other hidden patterns lie waiting for you to discover inside the geometric shapes of everyday numbers? Keep looking, keep calculating, and I truly hope this explainer has given you a whole new dimension of curiosity.
Welcome to This Explainer. So today we're going to completely rethink how we look at math. We're not doing dry formulas or stuffy textbook rules here. Instead, we're going to treat it like a really fascinating mystery that's just waiting to be unlocked. We're diving deep into the hidden magic, the secret patterns, and the incredibly rich history of cubes and cube roots. And we're going to cover everything from ancient Babylonian clay tablets all the way to the literal roots of plants. Let's just jump right in, because I promise you, numbers have way more personality than you might think.
To really show you what I mean by numbers having a personality, let's start with a legendary story. Picture this. The brilliant British mathematician G.H. Hardy goes to visit his colleague, the famous Indian mathematician Srinivasa Ramanujan, who happens to be lying ill in bed. Just trying to make some polite conversation, Hardy mentions that he rode over in a taxicab with a license plate number 1729, and he just casually remarks that it seemed like a pretty dull, uninteresting number, and he was kind of hoping it wasn't a bad omen.
Well, Ramanujan, literally without listing a single beat, replies, "No, Hardy, it is a very interesting number." He instantly saw something in that random four-digit string that completely went over his genius colleague's head. Today, 1729 is actually famous all over the world as the Ramanujan-Hardy number. So, what in the world did Ramanujan see?
Okay, the secret identity of 1729 is just mind-bending. Ramanujan instantly realized that 1729 is the absolute smallest number that you can express as the sum of two cubes in two completely different ways. Think about that. You can cube 1 and cube 12, add them up, and boom, you get 1729. Or you can take 9 cubed, add it to 10 cubed, and you also get exactly 1729. It's almost like a mathematical double agent.
Because of this amazing little interaction, any numbers that share this super specific property are now called taxicab numbers. And yes, there are more of them out there. The next two in line are 4104 and 13,832. How did Ramanujan just know this off the top of his head? Well, his colleague John Littlewood famously joked that every positive integer was one of Ramanujan's personal friends. He just intuitively felt the patterns. So challenge yourself for a second. How do you think these next two numbers break down into the sum of two perfect cubes?
Now, while Ramanujan was definitely a once-in-a-generation genius, numbers hold these beautiful, elegant patterns that honestly anyone can spot once you know what to look for. Consecutive odd numbers perfectly illustrate one of my absolute favorites. Check this out. The first odd number, 1, is just 1 cubed. Pretty simple. Add the next two odd numbers together, 3 plus 5, that's 8, which is exactly 2 cubed. Add the next three odd numbers, 7, 9, and 11, you get 27, which is 3 cubed. Add the next 4, and you guessed it, you get 64, which is exactly 4 cubed. The pattern is just flawless.
So let's see how this builds into a really fantastic brain teaser. Imagine handing someone this huge, intimidating addition problem. Most people would immediately reach for their phone calculator, right? But because you now know the secret pattern, you literally don't have to do a single bit of addition to solve this. All you have to do is count how many consecutive odd numbers are sitting right there. If there are exactly 10 numbers in that sequence, well, what do you think the sum is? It's just 10 cubed, 1,000. Seriously, advanced math is basically just a series of incredibly clever shortcuts.
All right, having seen how beautifully cubes build up, let's look at how we take them apart by defining their opposite. The cube root is simply the inverse operation of a cube. If a cube is a fully finished building, the cube root is the foundational blueprint you started with. So if a number y is created by cubing x, then x is our cube root. It's that core, base ingredient that you multiply by itself 3 times to get your final, three-dimensional result.
But practically speaking, how do you actually find that base ingredient?
Like, if you have a massive number, how do you test if it's a perfect cube? Well, we use a mechanical process called prime factorization, and you can think of it as a simple three-step recipe. Step 1, you completely break the number down into all of its prime factors. Once you've got those pieces, step 2 is to group any identical factors into triplets, groups of 3. Finally, step 3, you pull just one factor from each of those triplets and multiply them together.
Let's actually put this into practice. Take a number like 3375. If we break it all the way down, its prime factors are 3 3s and 3 5s. Notice how they group perfectly into neat little triplets? Awesome. So we grab 1 3, we grab 1 5, multiply them, and we instantly see that 3375 is exactly 15 cubed. But now, contrast that with the number 500. Its prime factors are 2 2s and 3 5s. Uh-oh, we are missing a 2. We can't form a triplet there. So this grouping method instantly exposes 500 as an imposter. It is definitely not a perfect cube.
So, the absolutely crucial takeaway here is this fundamental rule. Every single prime factor of a base number is going to appear exactly 3 times in the prime factorization of its cube. This pattern is wildly consistent. Just look at the number 6. Its prime factors are simply 2 and 3. When you cube 6 to get 216, its factors just scale up. They become 3 2s and 3 3s. It is a perfectly scalable, beautiful reflection.
Okay, let's step away from the pure mechanics for a minute and zoom out to look at the history, because humanity's obsession with these numbers literally goes back millennia. Long before anyone had a digital calculator in their pocket, ancient civilizations were fascinated by squares and cubes. I mean, as early as 1700 BCE, the Babylonians were actively compiling lists of them. Jumping way forward, the Indian mathematician Aryabhata formally defined the geometric square around 499 CE. And then, a little over a century later, Brahmagupta was writing about how roots formed the actual base of these shapes.
Seriously, just think about this incredible clay tablet from the Babylonians. This isn't just some dusty ancient artifact sitting in a museum. It is literally a prehistoric Excel spreadsheet. They spent time compiling these rapid mathematical lists of squares and cubes on wet clay just so they could quickly reference them for vital daily tasks. They desperately needed these calculations to measure land, design architecture, and solve the complex geometric problems required to literally build their empire from the ground up.
And there's this profoundly beautiful linguistic connection between nature and math that I just have to mention. In ancient India, they used the Sanskrit word mula for mathematical operations. Now, mula literally translates to a plant root, a base, or a cause. They visualized a square root as the literal physical root planted in the ground from which a geometric shape actually grows upward. This biological metaphor was so powerful that it was later translated into Arabic and then eventually into the Latin word radix, which also means plant root. It is literally why we call them roots today. So, math isn't just some abstract exercise trapped in a textbook. It's this living, breathing language of patterns that's been passed down from the ancient Babylonians to Ramanujan, and now directly to us. Which brings us right back to the present moment. I want to leave you with a bit of a challenge, to really encourage you to apply that exact same logic and pattern recognition we've been uncovering today. Have you ever heard of the adjacency square puzzle? It's this fascinating little numbers game. Take a look at this short sequence: 3, 6, 10, 15, 1. The main rule here is that any two adjacent numbers, so numbers sitting directly next to each other, have to add up to a perfect square. Let's check it. 3 plus 6 is 9, 6 plus 10 is 16, 10 plus 15 is 25, and 15 plus 1 is 16. It's essentially a really delicate mathematical chain where every single link forms a perfect square.
So here is your grand finale challenge to take away from this explainer. Can you figure out how to arrange the numbers 1 through 17 in a single row without repeating a single one so that every adjacent pair forms a perfect square? And hey, if you manage to crack that one, what if you tried arranging the numbers 1 through 32 in a continuous circle using that exact same rule? I highly recommend you grab a pen, clear off some desk space, and see if you can uncover some of your own mathematical magic. Always keep questioning the patterns of the universe. Thank you so much for joining me on this explainer, and I will catch you next time.
Great job! Now you know squares and cubes. Practice the questions and stay tuned for the next exciting math chapter. Subscribe for more learning.